How the Milky Way works, a deep lecture for sleep and relaxation. The Milky Way is the galaxy in which our gentle little solar system lives. It is our vast cosmic home, a slow-breathing ocean of stars, gas, dust, and invisible forces. For many centuries, humans have studied its structure, its origin, and the hidden patterns woven through its light. The first skywatchers called it a river of milk, a road of the gods, a luminous path across the heavens. And today, with the quiet patience of science, we know that it is a gigantic stellar system, more than 100,000 light-years wide, so large that even light, the fastest traveler in the universe, needs 100,000 years to cross it. Yet even now, with all our telescopes and equations, many mysteries remain. How did our galaxy form? What hidden processes move beneath its glowing surface? And what technologies might one day allow humanity to drift gently into its most distant regions? The structure of the Milky Way is made of several peaceful, layered components. At its very center lies the galactic core, a dense, crowded region of stars, gas, and glowing dust. Deep inside that core rests a supermassive black hole with a mass millions of tons greater than our sun. It is like a quiet, invisible heart holding the galaxy together through gravity alone. Surrounding the core is the bulge, a softly glowing spherical region filled with ancient stars, some of the oldest in the galaxy. From there, the great galactic disk stretches outward, forming beautiful spiral arms. These arms are the luminous ribbons we see when we look at images of distant spiral galaxies. And they are the same pattern we imagine our own galaxy to have. Beyond the disk lies the halo, a vast, faint sphere filled with ancient stars and shimmering globular clusters, floating quietly around the galaxy like forgotten lanterns in the dark. All together, these layers form a complex and deeply elegant system, a cosmic architecture shaped by time. Scientists believe that the Milky Way formed slowly over billions of years. One widely accepted idea suggests that our galaxy was built through the merging of many smaller proto-galaxies. These ancient collisions stirred space like a cosmic ocean, mixing matter, igniting waves of star birth, and creating enormous clouds of glowing gas. Today, using powerful space telescopes and radio observatories, astronomers can still see the remains of these ancient mergers. They appear as long, delicate streams of stars, drifting through the galaxy, gentle echoes of worlds that were absorbed long ago. Our galaxy is not perfectly smooth or symmetrical. In recent decades, astrophysicists have discovered that the disk of the Milky Way is slightly bent and even rippled like a soft wave. These distortions are caused by the gravitational pull of nearby dwarf galaxies. One of the most important of these is the Sagittarius dwarf galaxy, which is slowly being torn apart and absorbed by the Milky Way. As it dissolves, it leaves behind long trails of stars like cosmic footprints, forming what some scientists poetically call hidden pathways through our galaxy. A mysterious substance plays a silent but powerful role in all of this. It is called dark matter. We cannot see it, but we feel its gravity. Calculations show that most of the mass of the Milky Way is not made of stars or gas, but of this invisible material. This means that everything we see, the core, the disk, the spiral arms, is embedded inside a vast, unseen gravitational framework. In the future, understanding the distribution of dark matter may become essential for interstellar travel, because it shapes how spacecraft will move across the enormous scales of the galaxy. Human curiosity about the Milky Way is far older than modern science. Across the world, ancient cultures left behind stone circles aligned with the stars, temples aimed at the heavens, and myths of celestial roads. Some of these artifacts suggest astronomical knowledge far ahead of their time. Although these ideas remain speculative, they show that humanity has always felt a deep connection to the glowing band of the Milky Way, seeing in it both mystery and meaning. Today, we create detailed maps of our galaxy using advanced technology. One of the most important missions is Gaia, launched by the European Space Agency. It measures the positions and motions of billions of stars, allowing scientists to build a three-dimensional model of the Milky Way and trace its slow evolution. These maps reveal that stars move at different speeds, once again pointing to the presence of hidden mass. With every new map, more invisible structures emerge, quietly revealing paths we never knew existed. Looking to the future, one possible technology for exploring the galaxy is the interstellar light sail, a giant reflective sheet pushed forward by the pressure of starlight. Other ideas involve warp drives, based on bending space and time itself. Though still theoretical, these concepts show humanity's deep desire to move beyond its cradle and gently drift between the stars. Seen this way, the Milky Way is not just a collection of stars. It is a living, layered system, full of history, motion, and hidden pathways. A cosmic home that humanity is only beginning to understand. From Earth, the Milky Way appears as a pale, glowing band stretching across the night sky. It is made of billions of stars so closely packed that our eyes see them as a single mist of light. For thousands of years, cultures tried to explain this vision. The ancient Greeks imagined reflected starlight. Chinese astronomers called it a heavenly river. In India, it was the trail of divine beings. Today, we know it is a vast stellar city filled with stars, gas, dust, planets, and dark matter. The Milky Way rotates slowly and majestically. Stars move around its center at about 200 kilometers per second, and one full orbit takes roughly 200 million years. Our solar system has completed only a few dozen of these gentle revolutions since Earth was born. At the very center lies Sagittarius, a supermassive black hole millions of times heavier than our Sun. Stars orbited on stretched, graceful paths, allowing scientists to measure its mass and confirm Einstein's theories. The galactic disk is where most star formation happens. Gas and dust gather, gravity pulls them together, and new stars are born. These glowing nurseries are called nebulae, like the Orion Nebula, 1,300 light-years away, quietly creating new suns. And beyond all this lies the halo, filled with ancient globular clusters, each containing hundreds of thousands or even millions of stars. They are among the oldest structures in the universe, soft witnesses to the beginning of everything. When you look up at the Milky Way, you are not just seeing light. You are seeing the memory of time itself, drifting gently across the sky. The study of these ancient star clusters allows scientists to gently reconstruct the long and quiet history of how the Milky Way was formed. Of special importance is the distribution of dark matter inside the galactic halo. Calculations show that the mass of dark matter is tens of times greater than the mass of all visible stars combined. This mysterious substance does not emit light, and it does not reflect it. Yet its presence reveals itself through gravity. Without dark matter, the rotation speeds of stars at the outer edges of the galaxy would not match what we observe. Something invisible is holding them in place, like a silent cosmic skeleton supporting the glowing body of the Milky Way. Scientists believe that dark matter may be made of unknown elementary particles that we have not yet been able to detect directly. Understanding its true nature remains one of the greatest quests of modern physics. Observations also show that the Milky Way has a beautifully complex pattern of spiral arms. Astronomers identify several major ones: the Perseus arm, the Sagittarius arm, the Cygnus arm, and others. Our own solar system rests quietly on the edge of a smaller structure called the Orion arm, between Sagittarius and Perseus, a calm neighborhood inside this vast spiral. Each arm contains regions of active starbirth, young, hot, brilliant stars, and immense clouds of gas. Although these spiral shapes seem stable, they are not fixed structures. They are actually density waves, slow-moving patterns that travel through the galactic disk, gathering matter as they go, like gentle ripples on a cosmic sea. One of the most fascinating discoveries of recent decades is that the galactic disk is not perfectly flat. It is slightly bent, subtly warped, like a soft sheet floating through space. This deformation is likely caused by the gravitational influence of nearby dwarf galaxies. The most famous of these is the Sagittarius dwarf galaxy, which is slowly being torn apart and absorbed into the Milky Way. As it dissolves, it leaves behind long trails of stars, stellar streams, moving together through space, whispering stories of ancient encounters. Modern space missions have expanded our understanding enormously. The Gaia mission of the European Space Agency is mapping the positions and motions of more than 1 billion stars. With this data, scientists build a living three-dimensional model of the Milky Way and watch its slow evolution. These maps allow us to predict the future of the galaxy and even to simulate its encounters with others. The Andromeda Galaxy is the Milky Way's nearest large neighbor. It is also a spiral galaxy, about 2.5 million light-years away. Careful measurements show that Andromeda and the Milky Way are slowly drifting toward each other. In several billion years, they will gently collide, merging into a new, giant elliptical galaxy. For humanity, this event lies far beyond any imaginable future. Yet modeling it helps scientists understand how galaxies grow, change, and transform. The Milky Way also has many smaller companions. Among them are the Large and Small Magellanic Clouds, dwarf galaxies gravitationally bound to our own. They contain active star-forming regions and offer scientists valuable laboratories for studying how galaxies evolve. Our galaxy is part of a larger family called the Local Group, which includes dozens of galaxies linked by gravity. This group itself is part of even larger clusters and superclusters. So the Milky Way is woven into a vast cosmic web, stretching across millions and billions of light years. Studying the Milky Way is one of the central goals of modern astronomy. Even though we live inside it, scientists can still build global models of its structure. They do this by combining many kinds of light. Visible light shows stars. Infrared light passes through dust. Radio waves reveal hydrogen gas. X-rays expose powerful, energetic events. Each wavelength adds a soft, glowing layer to our understanding. Radio astronomy is especially important. Neutral hydrogen emits radio waves with a wavelength of 21 centimeters. These signals allowed scientists to map the spiral arms for the first time. Radio telescopes also measure the movement of gas, revealing how the galaxy rotates. When these motions did not match the visible mass, dark matter once again revealed its hidden presence. Infrared telescopes allow us to see through dust clouds that block visible light. They have revealed the bar-shaped structure of the galactic center and the distribution of stars in the bulge. X-ray and gamma-ray observations show the most violent events, supernova explosions and flares from the black hole at the galaxy's core. These energetic outbursts seed space with heavy elements, fueling new generations of stars. Magnetic fields also weave quietly through the Milky Way. They influence charged particles and help shape clouds of gas. Their patterns, measured through radio polarization, play a role in maintaining the spiral structure and regulating star formation. The Milky Way likely formed from tiny density fluctuations in the early universe. Over time, matter gathered, stars ignited, and small galaxies merged, slowly building the galaxy we see today. Distant galaxies, seen at high redshift, show us these early stages, small, chaotic systems growing into grand spirals. Some scientists believe that hidden gravitational connections between galaxies create ripples and stellar streams, leaving subtle fingerprints in galactic disks. These distortions are like cosmic memories, tracing every ancient interaction. Today, artificial intelligence helps astronomers analyze vast amounts of data. Machine learning finds patterns, rare objects, and hidden structures no human could see alone. And by studying the chemical signatures of stars, scientists learn their ages, their origins, and their journeys through time. Each star is a quiet archive of the galaxy's past, a glowing page in the endless story of the Milky Way. So, it became clear that within the disk of the Milky Way, there exist different generations of stars. The oldest stars contain very few heavy elements, while younger stars contain many more. This happens because each generation of stars, as it completes its life cycle, enriches the interstellar space with the products of nuclear fusion. In a quiet and beautiful way, stars seed the galaxy with the ingredients for future worlds. A particularly fascinating question is how planetary systems are distributed throughout the galaxy. Using the transit method and the observations of the Kepler Space Telescope, scientists have already discovered thousands of exoplanets. Statistical estimates suggest that the Milky Way may contain billions of planets located within habitable zones. Worlds where liquid water could exist, and perhaps life as well. This possibility opens a vast horizon for the search for extraterrestrial life and makes our galaxy an even more precious subject of exploration. Beyond direct observation, astronomers also use computer simulations. These digital universes allow them to recreate the evolution of the Milky Way over billions of years. The simulations include gravity, star formation, dark matter, and magnetic fields. By comparing simulations with real observations, scientists refine their models and better understand how our galactic home was born. The Milky Way is not isolated. It is surrounded by intergalactic gas, interacts with dwarf galaxies, and moves through cosmic streams. Matter and energy flow between galaxies, binding them together in the great dance of the universe. In this sense, our galaxy is part of a much larger story. The Milky Way is not only stars and gas, it is also a vast archive of cosmic history. Every region contains quiet traces of processes that took place billions of years ago. To reconstruct these events, astronomers use many tools, from spectroscopy to numerical simulations. One of the most important tasks is determining the precise age of the galaxy's structures. The oldest parts of the Milky Way are about 13 billion years old, nearly as old as the universe itself. These estimates come from globular clusters. Their stars are ancient, poor in heavy elements, and rich in hydrogen and helium, a signature of formation soon after the Big Bang. Astronomers divide stars into different populations based on their metal content. Population 2 stars are old and metal poor. They reside in the halo and globular clusters. Population I stars are younger and metal rich. They form the spiral arms and include our Sun. This distinction allows scientists to build a timeline of galactic formation. The galactic disk, where our solar system lives, is relatively young, about 10 billion years old. Yet it continues to form new stars even today. It likely formed from gas accretion and mergers with smaller protogalaxies. The evidence lies in stellar streams stretching across the disk, the lingering ghosts of ancient systems absorbed by the Milky Way. The central bulge is older than the disk and contains fewer heavy elements. Its bar-shaped structure channels gas inward, feeding star formation, and the supermassive black hole at the core. With each new generation of stars, the galaxy becomes chemically richer. Supernova explosions, red giant winds, and neutron star mergers create heavy elements that later form new stars and planets. This slow enrichment is called chemical evolution. The disk itself has both a thin and a thick component. The thin disk contains young stars and gas. The thick disk is older and more chaotic. Its age, about 12 billion years, suggests it formed during ancient galactic mergers. Stellar streams, long rivers of stars, trace the destruction of dwarf galaxies and clusters. They are hidden pathways through time, revealing the galaxy's past. Galactic archaeology uses chemistry, motion, and simulations to reconstruct how the Milky Way was built. In about 4 billion years, the Milky Way will collide with Andromeda. Stars will rarely collide, but their orbits will change, triggering new waves of star birth. Hidden waves move through the disk, caused by passing galaxies and intergalactic flows. Some models even suggest vast streams of dark matter flowing silently through the galaxy. And in all of this, humanity exists for only a brief moment. Yet, in that moment, we have learned to map the stars. And so, with each discovery, we step a little closer to understanding our cosmic home. One of the most beautiful features of the Milky Way is that it serves as a natural laboratory for exploring the deepest laws of cosmology and astrophysics. Because it is our home galaxy, we can observe it with a level of detail that is impossible for distant systems. Every careful study of its regions adds a small piece to our understanding of the universe as a whole. Much of what we know comes from studying stellar populations. Every star carries a memory of the time and conditions in which it was born. Through spectroscopy, astronomers can measure a star's temperature, mass, chemical composition, and age. If a star contains heavy elements like iron or calcium, it means it formed after many generations of supernova enriched the galaxy. Stars with very few metals belong to the oldest generations, quiet witnesses of the early universe. Red giants hold a special place. Their brightness is predictable, allowing them to act as cosmic candles. By comparing their true brightness to how bright they appear, scientists can measure distances and build three-dimensional maps of the Milky Way. This method forms the backbone of the Gaia mission, which has created the most detailed stellar map ever made. Star clusters also tell deep stories. Open clusters are young families of stars, born from the same cloud, sharing the same age and chemistry. Globular clusters, by contrast, are ancient and massive. Hundreds of thousands of stars bound together, orbiting in the halo, carrying the memory of the galaxy's earliest days. Astronomers also listen to the quiet vibrations of stars. This field, called asteroseismology, studies tiny pulsations on stellar surfaces. These rhythmic changes reveal a star's inner structure, mass, and age. Through these gentle tremors, scientists refine the timeline of how different regions of the Milky Way formed. Between the stars lies the interstellar medium, a soft ocean of gas and dust, hydrogen, plasma, and microscopic grains of carbon, silicon, iron, and frozen ices fill the space between suns. These particles absorb and scatter light, but they are also the raw material from which new stars and planets are born. In the densest places, Molecular clouds. Temperatures drop almost to absolute zero. Here, complex molecules form, and gravity quietly begins the process of star birth. Radio astronomers map these clouds using molecular signals, watching how they grow, move, and collapse. The galaxy breathes in cycles. Stars are born from gas and dust, and at the end of their lives, they return that material to space. Supernova explosions send shockwaves through the galaxy, compressing nearby clouds and triggering new generations of stars. In this way, the Milky Way is a self-renewing system, where creation and destruction are gently intertwined. In the heart of the galaxy, giant energetic bubbles, the Fermi bubbles, rise above and below the disk. They stretch tens of thousands of light years. Their origin remains mysterious, perhaps from the black hole's past activity or ancient waves of supernova. Either way, they tell us that the galaxy's core has not always been quiet. Even faint radio relics whisper stories of ancient collisions and powerful outflows. Sensitive new telescopes will soon listen to these echoes with unprecedented clarity. Everything in the Milky Way moves. Stars orbit the center. Gas flows, collides, and reshapes. Clouds merge and fragment. These motions are modeled with vast computer simulations, recreating billions of particles to test our theories of galactic evolution. Our solar system rests inside a region called the local bubble, a cavity of hot, thin gas created by ancient supernova. It is a gentle reminder that even nearby space is shaped by cosmic events. And among all this, astronomers quietly search for signs of life. With billions of planets in the Milky Way, the possibility of life feels softly real. Radio telescopes listen for artificial signals, so far in silence, but with growing hope. Gravitational waves open another door. They allow us to feel the universe, not just see it. Merging black holes and neutron stars send ripples through space-time itself. Future detectors may even sense events deep within the Milky Way's core. So slowly and gently, through stars, gas, radiation, and gravity, we continue to learn. The Milky Way is our cosmic home, vast, ancient, and still full of quiet mysteries, waiting to be heard. This discovery became one of the strongest proofs of the existence of dark matter. The stars in the Milky Way are not spread evenly. Beyond the spiral arms, there are also stellar associations, gentle families of young stars born from the same cloud, still traveling together, not yet drifting apart. These associations are delicate markers of recent star formation, allowing astronomers to trace the galaxy's most recent chapters. There are also star clusters, open and globular. Open clusters contain hundreds or thousands of stars living within the disk. They are young and slowly dissolve under gravity. Globular clusters, by contrast, are ancient, hundreds of thousands of stars floating in the halo, carrying memories from the early universe. By studying them, scientists glimpse the galaxy's first breaths. The chemistry of stars reveals even more. Every star forms from gas with a unique blend of elements. In its spectrum, fine lines whisper which atoms are present. Old stars contain very few heavy elements. Young stars shine with richer metals. Through this quiet chemistry, astronomers read the long story of galactic evolution. In recent years, many stellar streams have been discovered. These long, graceful ribbons of stars once belonged to dwarf galaxies or clusters that were gently torn apart by the Milky Way's gravity. Their orbits stretched into arcs, wrapping around the galaxy. By following these streams, scientists reconstruct how the Milky Way grew, slowly absorbing smaller systems. Infrared observations allow us to see through dusty veils. They revealed that the galactic core has a bar-like shape, a structure that channels gas inward, feeding star formation and stirring the heart of the galaxy. At the very center rests Sagittarius A*, a black hole 4 million times the mass of the Sun. It is quiet today, but ancient X-ray echoes suggest it once flared brightly, perhaps creating the immense Fermi bubbles that rise above and below the galactic plane. The interstellar medium is the galaxy's breath. Gas clouds give birth to stars. Supernovae return matter to space. Elements flow, cycle, and renew. This rhythm is called galactic breathing, a slow, endless inhale and exhale of creation. Cosmic rays whisper through the galaxy, high-energy particles born from explosions and galactic storms. They shape molecules, clouds, and perhaps even the chemistry of planets. Gaia's immense database now contains the positions, motions, and compositions of billions of stars. Through it, astronomers have uncovered the scars of ancient mergers, when the Milky Way absorbed large protogalaxies, reshaping its disk and halo. Future telescopes will listen even deeper. Vast optical mirrors, new radio arrays, and gravitational wave detectors will reveal the galaxy's quiet secrets with unprecedented clarity. Simulations show that one day, the Milky Way will merge with Andromeda. Two vast spirals will slowly dance together, forming a new elliptical galaxy, igniting waves of newborn stars. The study of galactic motion, galactic kinematics, reveals that stars do not move in perfect circles. Some travel on tilted, elongated paths. Thick disk stars wander more chaotically than thin disk stars, evidence of ancient turbulence and long-forgotten collisions. Gaia uncovered, a monumental event called Gaia Enceladus, a massive merger 10 billion years ago. It built much of the thick disk and halo. Stellar streams like Sagittarius and Hercules Aquila are living traces of those ancient encounters, hidden pathways through time. By tracing their motions, astronomers gently reconstruct the Milky Way's past, a galaxy still quietly telling its story in starlight and motion. This beautiful branch of research is known as galactic archaeology, the quiet art of reading the past written in starlight. Astronomers also study disturbances within the galactic disk. Stars near our sun do not move in perfect stillness. They ripple, like waves in a calm cosmic ocean. These waves may have been created when a small dwarf galaxy passed gently through the disk, sending long-lasting vibrations through thousands of light years, lingering for billions of years. They appear as subtle patterns in the motion and density of stars, soft echoes of ancient encounters. Dark matter holds a very special place in these studies. Its invisible distribution controls the motion of everything we see. Modern models suggest that the Milky Way is wrapped in a vast halo of dark matter, far more massive than all stars and gas combined. This halo extends far beyond the visible galaxy, quietly holding everything together with gentle gravity. Scientists search for dark matter particles in deep underground laboratories, listening for the faintest whispers, but so far, they remain hidden. Dark energy, too, is studied on the largest scales, shaping the expansion of the universe itself. Supernovae are among the galaxy's most powerful sculptors. When massive stars explode, they release heavy elements and powerful shockwaves, compressing nearby gas and triggering the birth of new stars. They are both endings and beginnings, connecting one generation to the next. The cosmic rays born in these explosions spread throughout the galaxy, gently influencing the interstellar medium. Gamma-ray telescopes trace their paths, revealing how these energetic particles shape gas and magnetic fields. Our solar system travels around the galactic center once every 200 million years. Over Earth's long history, we have completed about 20 full orbits, passing through spiral arms and quiet inter-arm regions. Some scientists believe these journeys may have influenced Earth's climate and even the evolution of life. Closer to home lies the local bubble, a region of thin, hot gas surrounding our solar system. It likely formed from a series of supernovae over the past 10 million years. It is bordered by denser clouds like Taurus and Perseus, rich in chemistry and quietly forming new stars. Astrobiology adds another layer of wonder. The Milky Way may contain tens of billions of planets, many of them within habitable zones. Telescopes like Kepler and TESS have already discovered thousands of worlds, suggesting that life may not be rare in our galaxy. Computer simulations now allow scientists to recreate entire galaxies. Billions of virtual particles model stars, gas, and dark matter, testing ideas about spiral arms, bars, and disk waves. These cosmic dreams reveal both past and future. In about 4 billion years, the Milky Way will merge with Andromeda, two spirals slowly embracing, forming a new, glowing elliptical galaxy. At the heart of it all lies star formation. Stars are born inside giant molecular clouds, cold, dark, and rich in hydrogen, carbon, oxygen, and tiny grains of cosmic dust. Temperatures drop close to absolute zero, allowing molecules to survive and slowly combine. Gravity gathers the gas, forming glowing protostars. One such nursery is the Orion Nebula, 1,300 light-years away, visible even to the naked eye, a soft shimmer where new worlds are being born. Stars form in families, which is why open clusters are so common. They share age and chemistry, making them perfect laboratories for stellar evolution. Over time, they drift apart, becoming part of the galactic disk. Small stars like our Sun shine for billions of years. Large stars live fast and die in supernova, enriching space with the building blocks of planets. Each new generation contains more heavy elements than the last, a quiet record of the galaxy growing older and richer. Through spectroscopy, astronomers read the light of stars, each element leaving its delicate fingerprint. From this, they mapped the chemistry of the Milky Way, tracing the slow, beautiful evolution of our cosmic home. One of the most important directions in modern galactic research is the study of stellar population density, how stars are distributed across different regions of the Milky Way. Inside the spiral arms, the density of stars is higher than in the quiet spaces between them. These glowing arms are where star formation is most active, where gas gathers and new suns are born. Our own solar system rests near the edge of a smaller structure called the Orion Arm, a gentle bridge between the great Sagittarius and Perseus arms. This location is calm and stable, a peaceful cosmic neighborhood, one that may have helped life to grow and endure. Projects like Gaia and the Sloan Digital Sky Survey collect enormous amounts of data about stars, their motions, and their chemical fingerprints. With these vast libraries of light, astronomers map the galaxy, trace stellar streams, and uncover the quiet memory of ancient mergers. A deep and beautiful mystery lies in the connection between dark matter and star formation. Dark matter forms the invisible gravitational framework into which gas slowly falls. Its distribution decides where stars will be born, how spiral arms form, and how the galaxy evolves. Without dark matter, the Milky Way could not remain stable for billions of years. Simulations of the future show that star formation is slowly declining, but not forever. New bursts of creation will come when galaxies collide. The coming merger with Andromeda will awaken vast clouds of gas, igniting a brilliant storm of newborn stars. Around nearly every star spins a quiet disk of gas and dust. From these soft cosmic rings, planets take shape. Telescopes like Kepler and TESS have revealed thousands of distant worlds, showing us that planets are not rare, they are everywhere. Billions of them may drift through habitable zones, waiting in the gentle glow of their suns. Cosmic rays and magnetic fields also shape the galaxy. Magnetic fields stabilize gas clouds, guiding their slow collapse. Cosmic rays drive chemical reactions inside them, helping form the molecules that will one day become planets and perhaps life. Now we drift deeper into the interstellar medium, the vast ocean between the stars. It is made of gas, dust, magnetic fields, and energetic particles. Neutral hydrogen fills the galactic disk, glowing softly, at a radio wavelength of 21 centimeters. Ionized gas shines in star-forming regions lit by ultraviolet light from young, hot stars. Hot gas glows in X-rays inside supernova remnants, while cold molecular clouds cradle newborn suns. Molecules like carbon monoxide, methane, and ammonia act as gentle tracers of chemical evolution. Interstellar dust is made of tiny grains, silicon, carbon, iron, and frozen ices. It dims starlight, creating dark lanes in the sky, yet infrared telescopes can see through it, revealing hidden nurseries. Magnetic fields thread through the galaxy, quietly guiding the motion of gas. Cosmic rays flow along these invisible lines, adding pressure and shaping chemistry. Stars are born from clouds of gas and dust, and in death, they return their matter to space. Red giants release their shells. Supernovas scatter heavy elements. Neutron stars and white dwarfs enrich the cosmic ocean. This endless exchange is called the galactic cycle, a slow, eternal breathing of the Milky Way. Powerful observatories like ALMA and the future SACO map this invisible universe with exquisite detail. They reveal how clouds form, how gas flows, and how galaxies stay alive. Even near our sun, the local bubble of hot, thin gas tells a story of ancient explosions. And far above and below the disk, galactic winds carry matter into the halo, reshaping the galaxy. The mysterious Fermi bubbles stand as glowing reminders of past eruptions from the galactic core. And within the dark clouds themselves, scientists have found complex organic molecules, amino acids, and the building blocks of life. This tells us something profound. The ingredients of life are scattered throughout the Milky Way, quietly waiting in the soft embrace of starlight. The possibility that these organic molecules can travel through space carried by comets and meteorites makes the idea of life beyond Earth feel even more real, as if the seeds of biology are gently drifting between the stars. And if you enjoy discovering such quiet wonders of the universe, remember to like and subscribe, so together we can continue exploring the deep, glowing mysteries of the Milky Way. Modern numerical simulations allow scientists to recreate the behavior of the interstellar medium. They include gravity, magnetic fields, cosmic ray pressure, and the cooling of gas. By comparing these models with real observations, astronomers learn which forces dominate on different scales. Some models show that turbulence shapes the clouds. Others reveal the powerful feedback of supernova. So the 9th chapter of our journey is devoted to the interstellar medium, the quiet foundation of the galaxy, the place where stars are born, chemistry evolves, and the Milky Way breathes. One of the most fascinating regions of our galaxy is its central core. Here, the most extreme processes unfold, a place of dense star clusters, swirling gas clouds, strong magnetic fields, and at its heart, a supermassive black hole. Though it lies about 26,000 light-years away, modern instruments allow us to study it in exquisite detail. At the center lives Sagittarius A*, a black hole with a mass about 4 million times that of the Sun. The motion of nearby stars revealed its presence, especially a star called S2, which orbits the black hole once every 16 years along a graceful ellipse. Its motion became one of the most beautiful confirmations of Einstein's theory of general relativity. Today, Sagittarius A* is quiet, softly glowing, far calmer than the blazing cores of distant active galaxies. But ancient echoes remain. The Fermi bubbles, vast lobes of high-energy radiation, rise tens of thousands of light-years above and below the galactic plane. They are thought to be the ghostly memory of a powerful outburst from the black hole long ago. Near the core, thousands of stars crowd into a tiny region. Young, massive suns shine beside ancient, fragile ones. Here, gravity and radiation are far stronger than anywhere near our home. Studying these extreme environments helps scientists understand how stars form, even under intense pressure. Gas clouds near the center move along unstable orbits, sometimes spiraling inward, feeding the black hole. These flows release bursts of energy, brief flickers of activity in the deep. Strong magnetic fields guide charged particles, shaping jets and directing cosmic motion. In 2022, the Event Horizon Telescope revealed the first image of Sagittarius A*, the shadow of the black hole against glowing gas. It was a moment of profound stillness and wonder, humanity glimpsing the edge of space-time itself. The galactic core also holds strange stars, young, massive objects where none should easily form. Their existence challenges our understanding and inspires new theories of star birth in extreme gravity. The core is not just a curiosity, it teaches us how black holes regulate galaxies. Sometimes they awaken, sending energy outward, shaping gas, triggering or suppressing new stars. The Milky Way is our nearest laboratory for these cosmic rhythms. Chandra, LM, Hubble, and the James Webb Telescope together weave a layered portrait of the galactic heart. To the story. In the future, we'll track gas near the event horizon, measure magnetic fields, and follow bursts of energy as they rise and fade. Through them, we will learn how black holes shape galaxies, and how galaxies shape black holes. The Milky Way center is not only our local mystery, it is a key to understanding quasars. They are waves of density. And the Orion Arm, the quiet spiral branch where our solar system gently resides. Our own arm is relatively small and lies between much larger ones. This delicate placement provides long-term stability. Through radio observations. The 21-centimeter emission line of neutral hydrogen allows astronomers to map the distribution of gas across the galactic disk. Molecular clouds, where stars are born, are traced through observations of carbon monoxide. Together, these methods make it possible to build three-dimensional maps and to measure the motion of matter through the spiral arms. One of the most fascinating discoveries of recent decades is that spiral arms are not perfectly symmetrical. They contain branches, bends, and dense knots of matter. In some regions, enormous star-forming complexes appear, such as the Cepheus Association or the Carina-Sagittarius region. These areas contain thousands of young stars and serve as natural laboratories for studying the earliest stages of stellar and planetary evolution. Spiral arms are also closely linked to the central bar of the Milky Way. This elongated structure exerts a gravitational pull that channels gas inward, stimulating the formation of spiral waves. Models show that the interaction between the bar and the galactic disk creates long-lived, stable spiral patterns, like gentle ripples, moving through a vast cosmic ocean. Some scientists believe that external influences also shape the spiral arms. Dwarf satellite galaxies, such as the Sagittarius dwarf galaxy, can disturb the disk and amplify spiral structures. Even interactions with intergalactic gas may subtly alter the motion of matter inside the Milky Way. These processes are confirmed by simulations and by observations of similar phenomena in other galaxies. A particularly important topic is the position of the solar system within the Orion Arm. As the Sun moves through different regions of this spiral structure, it encounters varying densities of stars, cosmic rays, and clouds of gas. Some scientists suggest that these passages may have influenced Earth's climate and even the evolution of life itself. Modern infrared observations allow astronomers to see hidden star-forming regions that are invisible in ordinary light. The Spitzer Space Telescope and the James Webb Space Telescope have revealed stunning images of molecular clouds and newborn star systems. These data help refine our understanding of how spiral arms form and how they connect to the larger processes within the galactic disk. Another important direction of research is the chemical composition of stars in the spiral arms. Young stars contain more heavy elements, showing that the galaxy is constantly enriching itself through stellar evolution. By comparing the chemistry of stars in different regions, scientists can reconstruct the long history of the interstellar medium. Of special interest are the so-called stellar ridges, long chains of young stars that form along spiral arms. They are created by shock waves that arise when gas flows through regions of higher density. These ridges serve as beautiful evidence of the density wave theory of spiral structure. The future of this research lies with new telescopes. The Square Kilometer Array will map hydrogen on enormous scales, while the Gaia mission will continue to measure stellar motions with exquisite precision. Together, these data will allow scientists to build the most detailed map of the Milky Way ever created. And so, the 11th chapter of our journey is devoted to the spiral arms, the glowing pathways of star formation, structure, and cosmic rhythm. Beyond the disk lies another vast domain, the galactic halo. This is a diffuse, spherical region surrounding the Milky Way, extending tens and possibly hundreds of thousands of light years. Within the halo reside ancient stars, globular clusters, stellar streams, an immense amount of dark matter. Though its matter is sparse, the halo plays a crucial role in the galaxy's gravity and stability. The stars of the halo belong to the oldest populations. They contain few heavy elements, showing that they formed in the early universe. Many of them originated in small protogalaxies that later merged with the Milky Way. Their orbits are chaotic and highly elongated, very different from the smooth rotation of stars in the disk. This reveals the violent, dynamic past of our galaxy. Within the halo, globular clusters hold a special place. These dense systems contain tens of thousands to millions of stars and can be over 13 billion years old, among the oldest objects in the universe. By studying them, astronomers reconstruct the early history of the Milky Way. In recent years, scientists have also discovered stellar streams in the halo. These long, faint structures form when dwarf galaxies or star clusters are torn apart by gravity. They stretch across tens of thousands of light years and serve as hidden pathways through the galaxy's past. One of the most famous is the Sagittarius stream, left behind by the Sagittarius dwarf galaxy as it merged with the Milky Way. Some halo stars contain almost no heavy elements at all. They formed soon after the Big Bang and preserve the primordial chemistry of the early universe. Through them, we glimpse the first chapters of cosmic history. The greatest mystery of the halo is dark matter. Its mass far exceeds that of all stars and gas combined. It does not emit light, yet its gravity shapes the galaxy. Without dark matter, the flat rotation curves of galaxies would be impossible. Modern models suggest that dark matter forms a giant spherical halo within which the visible Milky Way is suspended, like a luminous island inside an invisible ocean. Although scientists continue searching for dark matter particles, its existence is already clearly revealed through astronomical observation. The halo, with all its faint stars, streams, and invisible mass, is a vast archive, a silent memory of everything the Milky Way has ever been. And slowly, as we drift through these ancient structures, the story of our galaxy continues to whisper through the stars. In recent years, scientists have also begun to focus on the so-called hot gas coronae that surround galaxies. The Milky Way, too, is wrapped in such a glowing halo of gas. This gas reaches temperatures of millions of degrees and shines softly in X-rays, invisible to our eyes, but clearly seen by space telescopes. This hot corona is believed to play a crucial role in the exchange of matter between the galaxy and the vast intergalactic medium, acting like a gentle breathing membrane between our cosmic home and the universe beyond. By studying the halo, astronomers can refine the total mass of the Milky Way. Current estimates range from 1 to 2 trillion solar masses. The wide uncertainty comes from our limited knowledge of how dark matter is distributed. Yet these numbers are not just important for understanding our own galaxy, they also shape our view of cosmology as a whole. Projects such as Gaia and SDSS continue to gather vast amounts of data about halo stars. Through these measurements, new stellar streams are discovered and their properties are refined. In the future, next-generation observatories, such as the Vera Rubin Observatory, will reveal an even clearer, deeper picture of the Milky Way's extended structure. And so, the 12th chapter is devoted to the galactic halo, the invisible framework that shapes the galaxy's motion and long-term evolution. Within this faint realm lies a memory of how the Milky Way was born, how it grew, and how it continues to change. One of the most fundamental ways to understand the Milky Way is through its chemical evolution. This term describes how the composition of stars and interstellar gas changes over time. It is deeply connected to the cycles of stellar birth and death, as stars create heavy elements and release them back into space. At the beginning of the universe, after the Big Bang, matter consisted almost entirely of hydrogen and helium. Elements like carbon, oxygen, iron, and uranium did not yet exist. They were forged inside the first stars, where nuclear reactions slowly built more complex atoms. When these stars ended their lives as supernova, or when neutron stars merged, they scattered these elements into the cosmos, mixing them into the cold, quiet gas between the stars. This gentle cosmic recycling became the foundation of the Milky Way's chemical evolution. Different generations of stars contain different amounts of heavy elements. Old stars are metal poor, while young stars are richer in iron, calcium, and other elements. These differences appear as faint or strong lines in their spectra. By comparing them, astronomers can determine the ages and origins of entire stellar populations. A particularly fascinating topic is the study of metallicity gradients, how chemical composition changes with distance from the galactic center. Stars near the core are richer in heavy elements because star formation has been more intense there for a longer time. Farther out, in the quiet outer disk, enrichment has proceeded more slowly. Special attention is given to globular clusters. These ancient systems contain stars with very low metal content, showing they formed early in cosmic history. Yet even inside them, scientists now find chemical variations, evidence that even these seemingly simple systems experienced complex internal enrichment. Large surveys, such as Apogee and Gala, collect spectra from millions of stars. By comparing elements like magnesium and iron, astronomers can separate stars belonging to the thin disk, thick disk, and halo, reconstructing the galaxy's past. Some elements form only in the most extreme events. Gold and platinum, for example, are created when neutron stars merge. Observations of gamma-ray bursts and their glowing aftereffects confirm that these rare events play a vital role in enriching the galaxy. Every cosmic explosion leaves its own chemical fingerprint. The rarest stars, those with almost no metals, are especially precious. They preserve the chemistry of the earliest universe and even carry traces of the very first supernova. Through them, we glimpse the dawn of star formation itself. Chemical evolution is also shaped by the flow of gas between the disk and the halo. Winds from stars and supernova push material outward. Later, some of this gas slowly falls back, mixing and redistributing elements across the galaxy. This breathing cycle regulates star formation and keeps the Milky Way alive. Numerical models now simulate these processes in detail, tracking supernova, winds, and gas accretion. They reveal that chemical enrichment has never been uniform. Different regions evolved at different speeds, shaped by starbursts and galactic mergers. Chemical evolution also connects to the possibility of life. Rocky planets require heavy elements like silicon, iron, and oxygen. Stars rich in metals are more likely to host worlds like Earth. In this way, the story of atoms is also the story of potential life. Another powerful dimension of understanding the Milky Way is its dynamics. The galaxy is never still. Stars, gas, and dark matter are constantly in motion, their gravity shaping the galaxy's form and future. One of the first keys to this motion came from rotation curves, which show how fast material moves at different distances from the center. According to Newton's laws, the speed should decrease with distance if only visible matter existed. And yet, the galaxy whispers another story. Yet observations reveal something surprising. Far from the galactic center, the speed of rotation remains almost constant. This quiet contradiction became one of the strongest pieces of evidence for the existence of dark matter, an unseen mass whose gravity provides the extra pull needed to hold the galaxy together. Stars in the disk of the Milky Way move along nearly circular paths, but these paths are not perfectly cool. Spiral waves, the central bar, and neighboring galaxies gently disturb them, stretching and reshaping their orbits. In some regions, matter gathers more densely, and new stars begin to form more actively. These motions are revealed by the exquisite astrometric data from the Gaia mission. By measuring the positions and velocities of billions of stars, astronomers have discovered wave-like patterns and subtle resonances rippling through the disk. Special attention is given to the stars near our Sun. They form a local kinematic structure, groups of stars moving together like quiet schools of fish through the cosmic sea. Some of these motions reflect nearby disturbances, while others reveal events that shape the entire galaxy. In our region, astronomers have even detected traces of waves left behind by a dwarf galaxy passing through the disk long ago. At the heart of the Milky Way lies the galactic bar. This elongated structure exerts a powerful gravitational pull, redirecting gas and stars. It funnels matter inward, feeding the central regions, while also creating resonant zones where rings and spiral arms take shape. Models show that the bar plays a crucial role in sustaining the spiral pattern itself. The galaxy's companions also shape its destiny. The large and small Magellanic Clouds are slowly interacting with the Milky Way, stretching vast streams of gas through space. The most famous of these is the Magellanic Stream, a colossal river of hydrogen extending for hundreds of thousands of light years. It stands as glowing proof that our galaxy is a living, moving system. Mergers with dwarf galaxies leave long-lasting traces. Streams of stars and gas remain behind, forming delicate arcs that drift through the halo. By studying them, astronomers can reconstruct the paths of absorbed galaxies and even measure the mass of the Milky Way itself. One of the best-known examples is the ongoing merger with the Sagittarius dwarf galaxy, whose stars still flow through our galaxy like cosmic echoes of a slow collision. The halo itself is also in motion. Its stars travel along long, elongated orbits, moving at high speeds. Their distribution reveals the galaxy's past, a history of growth through countless encounters. By tracking these stars, scientists can map the invisible web of dark matter that shapes the galaxy's gravitational field. Modern simulations show that the Milky Way is not perfectly steady. Its disk bends and ripples, likely under the influence of the Magellanic Clouds and other satellites. These gentle distortions are seen in many galaxies, revealing that such motions are universal. Looking ahead, astronomers peer into the future. In a few billion years, the Milky Way will meet the Andromeda Galaxy. They will slowly merge, their stars reshuffled into a new, vast elliptical galaxy. Direct star-to-star collisions will be rare, yet gravity will rewrite the entire cosmic structure. Dark matter remains the silent architect. Without it, the galaxy could not remain stable for billions of years. Its distribution controls the motion of stars and the shape of the disk. Projects like Gaia and future observatories continue to refine our understanding of these motions. Their data feed into detailed models that explain not only the Milky Way, but the evolution of galaxies across the universe. The motion of gas is equally important. Clouds drift, collide, and collapse, forming new stars and enriching the galaxy with elements. Radio and infrared observations trace this flowing material as it weaves through magnetic fields and spiral arms. Thus, the 14th chapter reveals the Milky Way as a living system where stars, gas, and dark matter move together to shape its destiny. One of the most fascinating chapters in this story is the tale of the satellite galaxies. These dwarf systems are bound by gravity to the Milky Way, and their interactions create streams of stars and gas, disturb the disk, and enrich the interstellar medium. The most famous companions are the large and small Magellanic Clouds, visible to the naked eye from the southern skies. The large cloud lies about 160,000 light-years away, and the small cloud about 200,000 light-years. They orbit each other and together dance around the Milky Way. Their motion creates the Magellanic Stream, a glowing ribbon of hydrogen stretching over 200,000 light-years. Within these clouds, giant star-forming regions shine brightly. The most famous is the Tarantula Nebula, one of the largest stellar nurseries in the nearby universe. By studying these regions, astronomers learn how stars and clusters form under the influence of a massive neighboring galaxy. Beyond the Magellanic Clouds, dozens of faint dwarf galaxies surround the Milky Way. Sagittarius, Sculptor, Boats, and many others are dim and sparse, yet they are the building blocks from which our galaxy grew. The Sagittarius dwarf galaxy is especially important. It is currently being torn apart, its stars forming a vast stream through the disk and halo. Gia's data has revealed this structure. in stunning detail, clear evidence that the Milky Way is still growing. Other dwarfs leave similar trails, delicate arcs of stars moving together through space. From these patterns, astronomers can reconstruct ancient mergers and refine the galaxy's mass. The chemistry of these stars tells another story. Their elemental composition differs from that of the Milky Way's disk, confirming their external origin. Through this cosmic chemistry, astronomers practice galactic archaeology, uncovering the past written in starlight. And still, the satellites continue to shape us. As they pass through the disk, they create waves and bends that persist for billions of years. They also bring fresh gas, fuel for new generations of stars. So even in their quiet motion, these small galaxies help the Milky Way breathe, grow, and dream. Their material slowly flows into the Milky Way, quietly nourishing the ongoing process of star birth. The Magellanic Stream is a beautiful example of this cosmic exchange. Its mass reaches millions of solar masses of hydrogen, and in the distant future, it may become fuel for new generations of stars. One of the most important goals of modern astronomy is the search for new dwarf galaxies. They shine very faintly and are difficult to distinguish against the bright background of Milky Way stars. Yet thanks to projects such as the Sloan Digital Sky Survey and Gaia, dozens of previously unknown systems have been discovered. By studying them, astronomers refine the story of how our galaxy grew and interacted with its neighbors. Numerical simulations show that satellite galaxies move along complex paths inside the Milky Way's gravitational field. Their orbits slowly shrink due to dynamical friction, and in time, they are gently absorbed into the larger galaxy. This process has been occurring for billions of years, and it is still happening today. Interestingly, the satellites are not arranged randomly. Many of them lie along certain planes, suggesting a shared origin. They may have once been part of a larger system that was torn apart long ago. Future observatories, including the James Webb Space Telescope and the Vera Rubin Observatory, will continue to search for and study these faint companions. Their discoveries will help us understand how the Milky Way interacts with its neighbors and how this shapes its long-term evolution. Thus, the 15th chapter is devoted to the satellite galaxies of the Milky Way, witnesses of its past and active participants in its present. Together with our Sun, they form a vast, living, and ever-changing system. One of the most fundamental questions about the Milky Way is its mass. The mass of a galaxy is not only the total of its stars and gas, but also the enormous amount of dark matter that dominates it. Knowing this mass is essential for understanding the galaxy's dynamics, its evolution, and its interactions with other galaxies. We cannot weigh a galaxy directly. Instead, astronomers use several gentle methods. One relies on measuring the speeds of stars and gas clouds. According to gravity, their motion reveals how much mass is holding them in orbit. The flat rotation curve of the Milky Way where outer regions move just as fast as inner ones, points again to vast amounts of dark matter. Another method uses satellite galaxies and globular clusters. Their orbits within the Milky Way's gravity reveal how massive the entire system must be. Faster motion and greater distances require more mass to keep them bound. Studies of the Magellanic Clouds and other satellites have helped define the galaxy's mass. Today, estimates range from 1 to 2 trillion solar masses. Most data suggest about 1.5 trillion. Only about 10% is in stars and gas. The rest is dark matter. Mass is not spread evenly. At the center lie the supermassive black hole and dense star clusters. The disk holds most stars and gas. The halo contains globular clusters and the vast reservoir of dark matter. This halo is what gives the Milky Way its long-term stability. Gaia's measurements of billions of stars allow astronomers to map this invisible mass. They reveal that the halo is not perfectly spherical. It bears scars from past mergers. These subtle asymmetries gently influence stellar orbits and create ripples in the disk. Dark matter streams, regions of enhanced density, have also been detected through their gravitational effects. Studying them helps refine our models of dark matter itself. Gravitational microlensing offers another quiet tool. When a massive object passes in front of a distant star, its gravity bends light and briefly brightens the image. From these events, astronomers infer hidden masses moving through the galaxy. Knowing the Milky Way's mass also helps predict its future collision with Andromeda. Greater mass means stronger gravity and a sooner merger. It also determines the fate of satellite galaxies. X-ray observations reveal hot gas filling the halo. This glowing plasma contains a large portion of the galaxy's ordinary matter, helping solve the mystery of the missing baryons. Cosmological simulations tie all of this together: accretion, mergers, star formation, and stellar explosions. They show that the Milky Way is still growing, slowly gathering matter from the cosmic web. Thus, the 16th chapter belongs to the mass of our galaxy, the foundation of all its structure, motion, and destiny. And now, we return home. The solar system is a small part of the galactic disk, orbiting the center about 26,000 light-years away. Our sun moves at roughly 230 kilometers per second, completing one full orbit every 200 million years. As it travels, it drifts through clouds, spiral arms, and changing environments, each quietly shaping the long story of Earth and the life upon it. Over the entire lifetime of Earth, the solar system has completed only a few dozen full orbits around the Milky Way. Each of these long journeys carried us through very different regions, from the dense, glowing spiral arms to the quieter spaces between them. Scientists believe that these passages may have subtly influenced Earth's climate and the evolution of life. When the sun moves through regions with a higher density of stars, the flow of cosmic rays reaching Earth may increase. These energetic particles can affect the atmosphere, cloud formation, and even biological processes. Although these ideas are still debated, they reveal how deeply connected our planet is to the larger rhythms of the galaxy. The motion of the sun relative to nearby stars is also carefully studied. Our system lies inside the local bubble, a vast cavity of hot, thin gas created by ancient supernova explosions. This bubble is surrounded by denser clouds, including the Taurus and Perseus clouds. Using infrared and radio observations, astronomers map these invisible structures, learning what kind of environment our solar system is drifting through. In the far future, tens of millions of years from now, the Sun will leave its current location in the Orion Arm and slowly enter new regions of the galaxy. These migrations may bring changes, different levels of cosmic radiation, and varying chances of close encounters with other stars. At present, our solar system occupies a relatively safe zone. Closer to the galactic center, radiation is stronger, supernovae are more frequent, and gravitational disturbances are far more intense. Farther out, the galaxy becomes too thin, with fewer heavy elements needed for planets and life. Our location appears beautifully balanced, a quiet, stable harbor within a vast cosmic sea. Nearby stars also tell an important story. Within just a few dozen light years lie red dwarfs, white dwarfs, and stars similar to the Sun. Their distribution reveals the fine structure of the galactic disk. Especially fascinating are the exoplanets orbiting these stars. They help us estimate how common life might be in our neighborhood of the Milky Way. Motion of the solar system also influences comets. As we pass through denser regions, gravitational disturbances can send icy bodies from the distant Oort cloud toward the inner planets. Such comet showers may have delivered water and organic molecules to early Earth. Modern missions like Gaia track the motion of nearby stars with exquisite precision. From this data, astronomers reconstruct past and future trajectories. One famous example is the star Gliese 710, which will pass about 1 light year from the Sun in tens of thousands of years, potentially stirring the Oort cloud and increasing comet activity. The Sun also moves up and down through the galactic plane in a gentle oscillation with a period of about 60 million years. These vertical motions may affect the cosmic ray flux reaching Earth. Some researchers even link these cycles to mass extinctions in Earth's history, a reminder of how deeply life is woven into galactic motion. The solar system exists within the local interstellar medium, a mix of gas clouds, magnetic fields, and cosmic rays. Thanks to the Voyager probes, which have left the heliosphere, we now directly measure the conditions of interstellar space. Their data helps define the invisible boundary between our Sun's influence and the wider galaxy. Many scientists continue searching for galactic influences on Earth's climate. Some suggest that spiral arm crossings increase comet impacts. Others explore how cosmic rays may affect cloud formation. Though still debated, these ideas remind us that Earth's history unfolds inside a vast cosmic environment. Thus, the 17th chapter belongs to the position and motion of the solar system within the Milky Way, and how its slow journey shapes the conditions for life on Earth. Now we turn to the stars themselves. The stellar populations of the Milky Way are one of our most powerful tools for understanding its origin and evolution. Stars differ in age, chemical composition, and motion. From these differences, astronomers reconstruct the story of how our galaxy was built. 3 main populations are distinguished. First, the thin disk, home to relatively young, metal-rich stars on nearly circular orbits. Our Sun belongs here. Second, the thick disk, older stars, poorer in heavy elements, moving on more elongated paths. This structure formed during an earlier, more turbulent era. Third, the halo, the oldest stars moving in chaotic orbits surrounding the galaxy. Chemical composition acts as a cosmic clock. Old stars contain few heavy elements, formed before supernova had enriched the gas. Younger stars carry the fingerprints of many stellar generations. By measuring elements like iron and magnesium, astronomers determine stellar ages and origins. Some stars were not born here at all. They were captured from other galaxies during ancient mergers. Gaia has revealed a group of stars from the Enceladus merger about 10 billion years ago. These stars now form a large part of the thick disk and halo. Stellar streams, the remains of disrupted systems, trace their former paths. They also map the invisible skeleton of dark matter. Astroseismology lets us listen to stars. Tiny oscillations in brightness reveal their internal structure, age, and mass. Missions like Kepler and TESS have turned this into a precise science. Star clusters add another layer. Open clusters are young, revealing how stars are born. Globular clusters are ancient, containing hundreds of thousands of stars, some over 13 billion years old. Many were captured from other galaxies. Spectroscopic surveys like GALA and Apogee now analyze millions of stars, weaving together the grand, gentle history of our Milky Way. These vast databases allow astronomers to detect the most delicate differences between stellar populations and to build detailed maps of the galaxy's chemical evolution. They have revealed, for example, that the abundance of elements in stars depends on their position within the galactic disk. Near the center, stars are richer in heavy elements. Farther out, toward the edges, they become more metal-poor, as if the galaxy slowly fades from bright gold into softer silver. The study of stellar populations is also deeply connected to astrobiology. Young stars, rich in heavy elements, are far more likely to host planetary systems, including rocky worlds like Earth. This means that the thin disk, where such stars are common, is one of the most promising regions for life to arise. In contrast, the ancient stars of the halo, with their low metal content, are far less suitable for building habitable worlds. To continue discovering such facts and gentle mysteries about our galaxy, remember to like and subscribe to the channel. Many more journeys through the Milky Way are still ahead. Modern simulations show that the stellar populations of the Milky Way formed in several stages. First came the ancient halo stars. Then, through accretion and violent mergers, the thick disk took shape. Later still, the calm, rotating thin disk emerged. These epochs are written in the chemistry and motions of the stars themselves. Variable stars play a special role. Among them, Kephides are especially important. Their brightness changes in a perfectly predictable rhythm, making them cosmic lighthouses. Using them, astronomers mapped the spiral arms and refined the scale of the entire galaxy. Other stars have extreme properties, very low metallicity, or unusual orbits. They are like living fossils, preserving information from the earliest epochs of cosmic history. By studying them, scientists uncover how the Milky Way formed and which processes shaped the young universe. Thus, the 18th chapter belongs to the stellar populations of the Milky Way, whose ages, chemistry, and motions allow us to read the galaxy's past and softly glimpse its future. One of the most informative fields of modern astrophysics is the study of stellar streams. These are long, delicate ribbons of stars moving along similar paths. They form when dwarf galaxies or globular clusters are slowly torn apart by the gravity of the Milky Way. Their remains stretch into graceful arcs, tracing ancient collisions. Thanks to Gaia, dozens of hidden streams have been revealed. Each stream contains stars of similar age and chemical makeup, confirming their shared origin. One of the most famous is the Sagittarius stream. It comes from the Sagittarius dwarf galaxy, which is still being absorbed. This stream wraps around the Milky Way for tens of thousands of light years, passing through both the disk and the halo. Its shape has helped refine the mass and gravitational structure of our galaxy. Another example is the Hercules Aquila stream, made of ancient stars on elongated orbits. It traces a merger that occurred about 10 billion years ago. These stars are poor in metals, a signature of the early universe. Stellar streams are like hidden pathways through time. Each merger leaves its own thread, woven into the galaxy. By studying them, astronomers reconstruct the mass, composition, and trajectories of long-lost galaxies. Although streams are born from destruction, their stars can move together for billions of years. The gravity of the Milky Way keeps them aligned, even as spiral arms and the galactic bar slowly bend and ripple them. Modern simulations recreate this process. Thousands of virtual stars are released along an orbit, slowly stretching into a stream. By comparing these models to real data, scientists refine the galaxy's gravitational field and the hidden shape of dark matter. Streams in the halo are especially valuable. Since the halo is dominated by dark matter, any distortions in the streams reveal its invisible structure. Tiny bends and gaps may mark clumps of dark matter passing silently through. Some streams even show multiple branches, as stars escape in waves rather than smoothly. A smaller example is the Hyades stream, formed from an open cluster, gradually dissolving. Even small streams carry deep information about how stars slowly drift apart. Future telescopes, including the Vera Rubin Observatory and the SKA, will reveal even fainter, longer streams. They will help test the nature of dark matter and refine our understanding of the Milky Way's gravity. Thus, the 19th chapter belongs to the stellar streams, gentle echoes of ancient galaxies that allow us to read the hidden history of our own. One of the most fascinating structures of the Milky Way is its central bar. The bar is an elongated river of stars and gas stretching across the galactic center, linking the spiral arms. It is best seen in infrared light, where dust becomes transparent. The Milky Way's bar is about 27,000 light-years long and tilted about 20 degrees relative to the Sun. Within it, dense star clusters and gas clouds flow under gravity. The bar creates resonant regions where stellar orbits change their shape, quietly guiding the movement of matter through the galaxy. One of the most important effects of the galactic bar is the quiet redistribution of gas. Slowly, almost imperceptibly, it guides matter from the outer regions inward toward the heart of the galaxy. This calm inward flow feeds the central regions and gently stimulates the birth of new stars. It also helps sustain the activity of the galactic core itself. Because of the bar, the central areas of the Milky Way show a noticeably higher concentration of young stars and dense clouds of gas. These regions are not chaotic. They are alive, constantly renewed by a steady, patient supply of material. The bar acts like a cosmic conveyor, moving matter across vast distances, without sound, without light. The bar also plays a crucial role in shaping the spiral arms. Its gravitational influence creates slow-moving density waves that travel through the galactic disk. As these waves pass, gas is gently compressed and stars begin to form along their paths. Over time, these waves become the foundation of the spiral structures we see. In this way, the bar functions like an engine, quietly maintaining the existence of the spiral arms over billions of years. A particularly intriguing area of research explores the connection between the bar and the activity of the central black hole. As gas flows inward, it may occasionally reach Sagittarius A*, the supermassive black hole at the center of the Milky Way. This process, known as accretion, can trigger periods of increased activity, brief awakenings in an otherwise calm giant. Many scientists believe that the bar may have played a role in forming the Fermi bubbles, enormous structures of high-energy radiation extending tens of thousands of light-years above and below the galactic plane. These vast, ghostly lobes may be echoes of ancient outbursts, fueled by gas driven inward long ago. Observations show that the bar is not a rigid or permanent structure. Over time, it can slowly change its length, strength, and orientation. Computer simulations suggest that bars form naturally through gravitational instabilities in galactic disks. As they evolve, they grow stronger, redistributing matter and angular momentum. Far in the future, the bar may weaken or even dissolve, subtly reshaping the entire galaxy once again. Bars are not rare. More than half of all known spiral galaxies contain them. This tells us that bars are a natural stage in galactic evolution, a quiet, inevitable process rather than an anomaly. They help maintain dynamical stability and regulate the long-term flow of matter. Studying the Milky Way's bar is especially challenging because we are inside the galaxy itself. To map its structure, astronomers rely on infrared telescopes such as Spitzer and WISE. These instruments can see through thick clouds of dust and reveal the hidden distribution of stars. Data from the Gaia mission adds another layer, measuring precise stellar motions and helping refine the bar's shape and orientation. The bar also influences the chemical evolution of the galaxy. As gas from different regions mixes together, chemical gradients become smoother. This affects the composition of stars forming near the bar. Spectroscopic studies reveal that stars in this region show a wide range of heavy element abundances, a quiet record of a long and complex enrichment history. Modern models suggest that the bar also interacts with satellite galaxies. Their gravitational pull can strengthen or weaken the bar, subtly altering its structure. For example, interactions with the Sagittarius dwarf galaxy may have influenced the bar's length and alignment. The future of this research lies with the next generation of observatories. Telescopes such as the James Webb Space Telescope and the Vera Rubin Observatory will allow astronomers to study the bar in greater detail than ever before. Radio observatories like LA and the Square Kilometer Array will trace gas flows and star formation with remarkable sensitivity. Together, these observations will slowly assemble a complete picture. Thus, this chapter is devoted to the bar of the Milky Way as a fundamental element of its structure. Its role in redistributing matter, shaping spiral arms, and sustaining central activity helps us understand not only our own galaxy, but spiral galaxies everywhere. One of the most fundamental and quietly powerful areas of Milky Way research is the study of its magnetic field. Though invisible, this magnetic field strongly influences the motion of gas, the propagation of cosmic rays, and the process of star formation itself. It threads through the entire galaxy, forming an essential component of the interstellar medium. The magnetic field of the Milky Way is measured indirectly. One of the primary methods involves observing the Faraday effect, gentle rotation of the polarization of radio waves as they pass through ionized gas immersed in a magnetic field. Through this subtle signal, astronomers slowly trace an unseen structure that quietly shapes the galaxy from within. By measuring this gentle rotation, scientists can determine both the direction and the strength of the magnetic field. Another important method involves studying polarized emission from interstellar dust in the infrared range. When these datasets are combined, they reveal a detailed and coherent picture of how the magnetic field is distributed across different regions of the galaxy. Observations show that the Milky Way's magnetic field has two main components, a regular one and a turbulent one. The regular magnetic field is aligned with the spiral arms, softly following their curved shapes, as if tracing the galaxy's long, winding structure. The turbulent component is connected to local processes, supernova explosions, stellar winds, and the continuous motion of interstellar gas. Its characteristic scales range from just a few parsecs to hundreds of parsecs, creating a complex, restless texture within the calm galactic flow. On average, the strength of the magnetic field in the Milky Way's disk is only a few microgauss. This is extremely weak compared to Earth's magnetic field, yet its influence is profound. Even such a delicate field can strongly affect the dynamics of gas. Magnetic fields can stabilize clouds, slowing or preventing their collapse, or gently guide compression along preferred directions. Because of this, magnetism becomes a key factor in the quiet process of star formation. Magnetic fields also play a crucial role in the journey of cosmic rays. Charged particles bend and twist as they move through magnetic fields, spreading gradually throughout the galaxy. This diffusion explains why cosmic rays reach Earth almost uniformly from all directions, even though their sources are concentrated in specific regions. At the same time, magnetic fields help trap cosmic rays within the galaxy, preventing them from escaping too easily into intergalactic space. Particularly fascinating is the structure of the magnetic field in the central region of the Milky Way. There, astronomers observe powerful vertical filaments stretching hundreds of light years above and below the galactic plane. These mysterious threads are likely connected to the activity of the central black hole and ongoing accretion processes. Studying them helps scientists understand how magnetic structures form and evolve under extreme conditions. The halo of the Milky Way also contains a magnetic field. Its strength is much lower than in the disk, but it extends tens of thousands of light years into space. This field plays an important role in how the galaxy interacts with the intergalactic medium. It can guide streams of gas and influence the motion of satellite galaxies, shaping the galaxy's extended environment. Modern projects, such as the Alophor Observatory, allow astronomers to map magnetic fields with unprecedented precision. These observations are used to build three-dimensional models of galactic magnetism. In the future, the square-kilometer array will provide an even more detailed view, detecting extremely faint signals and revealing fine-scale structures within the field. Another deeply interesting direction is the study of the origin of magnetic fields themselves. It is believed that they began in the early universe as extremely weak seed fields. Over time, turbulence in the gas and the rotation of galaxies amplified them to their present strengths. This process is known as the dynamo mechanism. Models show that such a dynamo can sustain magnetic fields for billions of years, quietly powering their persistence. Magnetic fields are also linked to chemical evolution. They influence the motion of dust and molecules, shaping the conditions under which complex compounds form. In some regions, scientists observe a clear correlation between the direction of the magnetic field and the shapes of interstellar clouds. This confirms that magnetic processes play a fundamental role in structuring the interstellar medium. For astrobiology, magnetic fields are important as well. They can help shield planetary systems from excessive cosmic radiation, reducing its impact on atmospheres. At the same time, they influence how radiation is distributed throughout a system, subtly affecting planetary environments. To continue learning about these hidden forces that shape life in our galaxy, feel free to like the video and subscribe to the channel. Your support helps the project grow and allows us to share new discoveries. Thus, the 21st chapter is devoted to the magnetic field of the Milky Way. This invisible yet powerful component plays a key role in galactic dynamics, chemical evolution, and long-term stability, quietly connecting countless processes within our cosmic home. One of the most intriguing areas of Milky Way research is the study of cosmic rays. These high-energy particles fill the entire galaxy and play an important role in its physics. Although cosmic rays were discovered more than 100 years ago, their origins and propagation mechanisms remain active topics of debate. Cosmic rays consist mainly of protons and helium nuclei, along with heavier nuclei, electrons and positrons. Their energies span an enormous range, from millions of electron volts to values exceeding 100 quadrillion electron volts. Such energies are far beyond the reach of human-made accelerators, making cosmic rays a unique probe of extreme cosmic processes. The primary sources of cosmic rays in the Milky Way are believed to be supernova. When a massive star explodes, it creates a shock wave that accelerates particles to high energies. This process is known as first-order Fermi acceleration. Observations of supernova remnants confirm the presence of accelerated particles through gamma-ray emission, a clear signature of high-energy protons interacting with gas. Other possible sources include pulsars and magnetars. Their intense magnetic fields and rapid rotation create powerful environments for particle acceleration. Additionally, processes near the Milky Way's central black hole may also generate cosmic rays, particularly those with extremely high energies. The propagation of cosmic rays through the galaxy is governed by interactions with the magnetic field. Charged particles follow complex, winding paths, scattering repeatedly on irregularities in the field. As a result, their motion resembles diffusion rather than straight travel. This explains why cosmic rays arrive at Earth almost equally from all directions. Cosmic rays also influence the interstellar medium itself. They exert pressure comparable to that of gas and magnetic fields, contributing to the overall balance of forces. In this way, cosmic rays help regulate star formation. They also ionize gas within molecular clouds, altering chemical reactions and promoting the formation of complex molecules. On Earth, cosmic rays interact with the atmosphere, producing cascades of secondary particles. These particles are detected by instruments on the ground and in space. Some studies suggest a possible link between cosmic ray intensity and climate variations, though this remains under discussion. Modern observatories, such as the Pier Auger Observatory and the Fermi Gamma Ray Space Telescope, study cosmic rays across a wide range of energies. Gamma ray observations are especially valuable, as they reveal regions where accelerated particles interact with gas. One of the greatest mysteries remains the origin of ultra-high energy cosmic rays. Their energies are so extreme that even the galaxy's magnetic field cannot contain them. They likely originate beyond the Milky Way, but studying them requires detecting extremely rare events. To understand the role of cosmic rays in the evolution of the Milky Way, scientists develop detailed numerical models. These models include particle sources, diffusion, and interactions with gas and magnetic fields. They show that cosmic rays can significantly slow cloud collapse, regulating the pace of star formation. Cosmic rays are also relevant to astrobiology. While high-energy particles can damage molecules, they can also trigger chemical reactions leading to new compounds. In some scenarios, cosmic rays may even have contributed to the synthesis of organic molecules on early Earth. To continue exploring these invisible flows of energy in the universe, feel free to like the video and subscribe. Ahead, we will share new discoveries about the hidden forces shaping our galaxy. Future research will rely on new observatories. The Cherenkov Telescope Array will observe gamma radiation with high precision, revealing new sources of accelerated particles. Advances in ground-based detectors will allow scientists to record even rarer cosmic ray events. Thus, the 22nd chapter is devoted to cosmic rays as one of the most important components of the galaxy. Silent messengers of extreme energy, filling the Milky Way and shaping its balance from within. Their origin, their long journey through the galaxy, and their influence on the interstellar medium reveal just how deeply they are connected to the evolution of the Milky Way and to the conditions that make life possible. One of the key directions in studying the Milky Way is understanding its evolution as a single, unified system. Our galaxy did not always look the way it does today. It formed slowly, over more than 13 billion years. The processes that unfolded in its distant past continue to shape its present structure, its motion, and its chemical composition. The formation of the Milky Way began shortly after the Big Bang. The first protogalaxies were vast clouds of dark matter and hydrogen. Under the quiet pull of gravity, these clouds gradually collapsed, giving birth to the very first generation of stars. These early stars were massive and short-lived. When they ended their lives in powerful explosions, they enriched the surrounding space with heavy elements, preparing the environment for future generations of stars. Modern models show that the Milky Way grew through a series of mergers with smaller systems. Each of these encounters left subtle traces, stellar streams, asymmetries, and distinctive chemical signatures. Data from the Gaia mission has allowed astronomers to reconstruct some of these ancient events. One of the most significant was the Gaia-Enceladus merger, which occurred around 10 billion years ago. This event contributed to the formation of a large part of the thick disk and the stellar halo. The evolution of the galactic disk itself unfolded in stages. First came the thick disk, composed of old stars with low metal content. Later, as the galaxy became more stable, the thin disk began to form. This younger disk contains stars rich in heavy elements and displays the graceful spiral structures we observe today. This process is still ongoing as new stars continue to be born within cold molecular clouds. The central bar and the galactic core formed as a result of gravitational instabilities. The bar redistributes gas, gently feeding the central regions and sustaining their activity. At the heart of the galaxy lies a supermassive black hole, whose growth is tied to the slow accretion of surrounding matter. Periods of heightened activity alternated with long phases of calm, leaving imprints in the structure of the interstellar medium. Interactions with satellite galaxies have played a particularly important role. Over its lifetime, the Milky Way has absorbed dozens of dwarf galaxies. Their stars now form part of the halo and extended stellar streams. Observations show that this process is still ongoing. The Sagittarius dwarf galaxy, for example, is currently being torn apart by tidal forces. Such interactions disturb the disk, creating bends, ripples, and large-scale waves. The evolution of the Milky Way is closely linked to chemical processes. Each generation of stars enriched the interstellar medium with new elements. As a result, younger stars contain more metals than older ones. This gradual enrichment is known as chemical evolution. By analyzing stellar compositions, astronomers can trace how the chemical balance changed across different regions of the galaxy. Importantly, galactic evolution has not been uniform. There were periods when star formation was intense, followed by quieter phases. These fluctuations are connected to gas inflow, interactions with other galaxies, and internal dynamics. Models suggest that star formation peaked around 8 billion years ago and has been slowly declining ever since. The future of the Milky Way is also shaped by evolution. In about 4 billion years, our galaxy is expected to merge with Andromeda. This encounter will give rise to a new massive galactic system. Although direct collisions between stars are unlikely, stellar orbits will be rearranged, and star formation is expected to increase. Galactic evolution is also studied in a broader cosmological context. The Milky Way is part of the local group, which includes Andromeda, the Triangulum galaxy, and dozens of smaller companions. The future of this group will be determined by gravitational interactions and the distribution of dark matter. To continue exploring these ideas about the past and future of our galaxy, feel free to like the video and subscribe to the channel. Your support helps the project grow and allows us to keep sharing new discoveries. Modern observations and simulations now allow us to look deep into the Milky Way's past. By comparing stellar chemistry, motions, and spatial distributions, scientists can reconstruct events that occurred billions of years ago. These insights reveal how the disk, the bar, the halo, and the core were formed. Thus, the 23rd chapter is devoted to the evolution of the Milky Way as a unified system. It shows that our galaxy is the result of complex processes, mergers, accretion, star formation, and chemical transformation. Processes that continue quietly, shaping our cosmic home even now.